and some familiar faces. Cool. Okay. The first thing I'd like to say is thanks for joining. Wanted to look at the schedule. Now, I mentioned today that I would give a little bit of a blip on sample size, effect size, and power analysis in experimental design. And in my mind, I thought, God, we talk about this all the time, and people are just going to be sick of it. But because we took a break over the summer, and because I'm old, I forget how long it has been since we talked about this stuff. And I think we have talked about particular power analyses within the last 12 months. But when I went back to look at the last time I gave a basic overview of the philosophy of power analysis, I was astonished. I won't tell you how long ago it was. I'll show you how long ago it was in just a second. So on meeting 131, our 131st convention of the Herrig meetings, we're going to talk about the basics of effect size and power. Because I have been asked sort of a lot of times, maybe about 5 or 6 people have asked me for power analysis. That's more than usual. I usually get about 1 to 4 per month, but I've had an awful lot in the last 2 weeks. I've invited Charlotte today, who's going to speak to us about her experiment, and then we'll discuss right at the end of today a full speed kind of practical warts and all way that we calculate power for a real experiment she's working on for her PhD. If there are any comments or questions during the talk, I think what the plan will be is I'm going to give some slides that are just an overview of what we talk about when we talk about power analysis and sample size, just as a refresher. And then I'm going to hand it over to Charlotte. She's going to explain her experiment, and then it'll come back to me, and we'll talk about, and I'll demonstrate the actual power analysis that I did for her experiment recently. And I should also say that this experiment is on cows, large animals, and we have an ethical, legal responsibility to justify the sample size for such experiments. But it's best practice for all scientists. You don't want to waste your time and either collect too much data or too few data, but there's a special legal requirement for animals, including the human animal, of course, in medical trials. And a lot of these stats tools were motivated by research on humans for ethical reasons. Okay, so without further ado, I'm going to start the slides, starting with mine. And I'm going to unshare my screen and reshare it the way that I like to present my slides. And here I come with the share. And now you guys should be able to see my screen. I'm going to go to the first slide. All right. Well, this is a slide from 2019, October 16th, which is the last time that I talked about power formally in an introductory way with slides. And astonishingly, I discovered this was our very first meeting that we ever had. So I couldn't believe it. Naturally, I've recycled some of these slides. So here's the new slide I've updated for today. You'll be glad to know that I shortened the slides by about 2/3. So I'm just going to present really the basics of thinking about effect size and power analysis for experimenters. So what we're going to talk about is what I mean when I say effect size thinking, what we're going to talk about when I say power calculation. I'm not actually going to demonstrate it in R today. We'll mention some R tools, but it's quite easy to do basic calculations in R. It's also quite easy to do basic calculations in some other tools. And I've decided today for today's meeting, because the calculation I'll explain is in some ways there are some subtleties that are hard, and in other ways there are some subtleties that are quite straightforward. So I've used a different piece of software than R that's free and openly available and open source, and I'll demonstrate that today, that I prefer for the subtle design that we're doing today. I've also dropped some breadcrumbs of resources and readings if you like that sort of thing. And oh, I don't think we're doing this today. That was for the first meeting. Okay, so onward. Now, there's a researcher, he's the first author in this paper, who is a friend of mine, Shinichi Nakagawa. He is a really good biostatistician, and his superpower is explaining complicated statistical ideas to non-statisticians really clearly. And he's got a great paper. It's a bit long in the tooth now, but it's still very relevant and modern. Effect size, confidence interval, and statistical significance, a practical guide for biologists. So I recommend that. But I wanted to step through really slow what is meant by effect size. And one complication, as I'll talk to you about in thinking about this, is that for every kind of statistical question or experimental question, there's a different way to philosophically think about effect size. And there's also a different way to calculate your expected effect size. So I'm going to just give one kind of effect size and power for this. I think I'm going to turn on my pen so that I can mark up the place. Now, for this kind of effect size, this is one of the simplest cases where we have a difference between these two means. Whatever is on the x-axis down here is a categorical variable. Maybe that variable has two levels, maybe one of them is a control, and we're measuring something. So this might be the control and this might be the treatment. Over here, we're measuring something quantitative that's on a scale that increases like that. And over here, these box plots symbolize the central tendency for that measure of the y variable for each of the treatments. When we think of effect size for this kind of experiment, we have to consider a couple of things. One, if we measure the means, these lines right in the middle of the boxes, one of the ways to quantify one of the essential bits that we need to quantify the effect size is the difference between those means. And the other bit of information we need is the variation around these means. Okay, it's like the whiskers on the box plot here. Now, in general, the bigger the difference is, the bigger the effect size, and the smaller the variation is, the bigger the effect size. So we can calculate I think I will have some more details about this in the next slide, but for this kind of effect size, for this kind of experiment, the quantity we use to estimate it is called Cohen's d, and it's that difference divided by the pooled standard deviation. Every statistical test, this is the annoying thing about effect size, every statistical test has a different variable and a different way of calculating the effect size. So just a few slides to really put a point on that. You can see over here in situation A, the means are not very different. And over here in situation B, the means are very different. So, we have to quantify with an expectation when we're designing an experiment how big that difference is. It's one of the hardest things when somebody comes to me or you just are thinking about it on your own. The hardest thing is that you have to have an estimation of this. You must have either pilot data or you must have bravery. to estimate how big that difference is. Nobody, no statistician is going to be able to do that for you because you are the expert. Most people don't have that, and so this is something that requires deep thought. This graph, or this slide, shows two graphs, situation A and situation B. And in this situation A, the variation is huge. But the mean difference is exactly the same. It's the variance that's different. So here, the situation B has a much larger effect size. Here we can resolve the difference between these means because the accuracy of estimation around that mean is very small. Here, and this is very pleasingly logical, the variation is so big we can't resolve those means accurately, and so the effect size calculated would be very small. Yet another consideration, even if we have very tight estimation, both of these, situation A and B again, both of them have very small variation for the estimation of the means. In one, the mean difference is very big, and in one, it's very small. We have to ask ourselves, now, is our expected effect size, remember it's relative to the variation, is the mean difference important biologically, or maybe medically, or maybe environmentally? So if we had a sample size, you're in complete control of your sample size as a researcher, and for some kinds of experiments, big sample sizes are easy to achieve. And one of the things, this is a bit counterintuitive perhaps to working scientists, is that if you have a too large sample size per the design of your experiment, you are sure to find a difference, even if that difference is insignificantly small and meaningless in the real world or meaningless to your own question. So it's one of the other things we think about when we think about effect size thinking. All right, so as I mentioned, the technical definition for this kind of experiment is Cohen's d, and we calculate it thusly. We take the mean of one quantity, subtract it from the mean of the other quantity. Usually we would take the absolute value of that, and then use the pooled standard deviation. Now, the pooled standard deviation is if the sample size is exactly the same for both of our samples here, sample 1 and sample 2, and if the sample size is the same for those samples, and if the standard deviation for each sample is exactly the same, the pooled standard deviation is simply an average standard deviation. But if it's not, if the sample sizes are different, or if they differ from one another, then it's a weighted average. Okay, we don't even need to go into the technical details of that for today. I wanted to point out two classic papers for this. You would have noticed that I mentioned that the quantity we just talked about was called Cohen's d, and this was defined by Jacob Cohen. He wrote a very influential book that, pardon me, this is a copy of the book. I've worn my copy out over the years as a reference. Now, he wrote this a long time ago, 1988, and it's still relevant today. It's still referred to. It's one of those rock star citations that crosses many scientific disciplines. Something like 40,000 citations were estimated on it. He also wrote a few very influential papers, and this is one of them. It's called A Power Primer. It's a classic. Would I recommend you read it? Maybe. If you like reading classics, it's one that should be on your top 100 as a PhD student, probably. It's one of those influential papers that you'd probably do well to cite. Another one is another paper by Shinichi, who it's got a great title, A Farewell to Bonferroni. That's a little statistical dad joke in the title. The Problem of Low Statistical Power and Publication Bias. Now, Cohen talked about the importance of power for doing good science. And Shinichi wrote this paper, also very highly cited. It's a modern classic, a little bit, quite a lot newer than Jacob Cohen's papers, to bring it to biologists. Both of these are great papers, highly recommended. So just moving along, we're interested in power because we want to know how many subjects we should have in our experiments. I mentioned for animals, there's a legal compunction for you to justify how many subjects you use. But I mean, there are other reasons. I'm not going to elaborate on all of them here today. We need to justify the sample size. Both the maximum and the minimum sample size should be justified under best practice, but we usually are looking for the minimum sample size to use. Why are we doing that? Well, this grid kind of spells it out. Up here is the real world, where you have a hypothesis, and this is kind of the stilted language of statistics. If your null is false, that means your hypothesis is true. The thing you believe to be true is true. And over here, so this is the real world on the columns, where in the real world, the null is true or the null is false. And over here is your conclusion after you perform some statistics. And you'll either conclude that you were wrong and the null is true, or you were correct and the null is false. Now, the two choices we'll look at first are if you were wrong, if the null is true and there's no difference, and you conclude there's no difference, hey, that's correct. I want to say that's a win, but a lot of scientists would view that as a fail because you were wrong. Down here is the best possible outcome. Your hypothesis was correct, and you statistically analyze it, and it supports the fact that your hypothesis is correct. But it's these two other corners we're interested in. One of them, the first one we'll talk about, is the type 1 error. I'm not going to give a full lecture on this. We could give a full lecture just on this little grid here today. But a type 1 error is when you have a false positive. The null is true, but you actually reject the null. And the probability of committing a false positive is the alpha value. And we call that the alpha error, or the type 1 error. And you're in control of this, believe it or not, as an experimenter, as a data analyst, even as a scientist and non-statistician. But by convention, even though you're in complete philosophical control over it, we all pick 0.05 as the maximum probability that we can accept of committing a false positive error. So that's the alpha value, so-called, and that is the value we compare our calculated p-value to. And if our p-value is below 0.05, we reject the null. That's where that comes from. Now, the type 2 error up here is a false negative. This is when you're correct. Your hypothesis is correct, but you fail to reject the null. This is the worst possible outcome. Now, you're also in complete control of this one, and in practice, working scientists do assume responsibility for it in almost all cases, because this rate of error is controlled by your sample size, 100%. So a bit of a weird thing is that the probability of this type 2 error is referred to as beta, juxtaposed with alpha. That makes sense. But what we actually talk about when we talk about type 2 error is power. And power equals 1 minus beta. So the minimum standard that is acceptable for statistical power is 80%. That's what we want to shoot for. That means that beta, the maximum beta we're by convention willing to accept is 20%. Usually for some studies, if you don't have any, assuming there's no constraint for sample size, some kinds of studies might require a much higher power if there is some kind of ethical or other kind of transgression that would be possible if it were set to the minimum baseline. But generally, it's 0.8. So as I mentioned, the type 1 error is controlled by you, the researcher, philosophically speaking, but in reality, convention of our practice of science demands that we choose 0.05. You're choosing this to convince the reviewer. Now, type 2 error is also controlled by you, like I said. I have said verbally that it's called beta, and it's the probability of failing to detect the difference that is real. Calculate power as 1 minus beta, and that 80% power is the standard minimum. All that's important enough to say twice. Got just a few slides here. One is that in the next few slides, a point I want to make is that for every kind of statistical test, there are different formulations of effect size, and Cohen's d is the very simplest one. This is just a screenshot, despite the invitation to slide me. Cohen, when he published this paper, I'm not going to go into this very much today, but we will refer back to it. He, for the different types of effect size, he proposed rules of thumb. I don't like rules of thumb very much. I like them less today than I did 5 years ago, and I like them much less today than I did 20 years ago as a student. Rules of thumb are dangerous because they can be used in ignorance and lead to big problems. But yet, Cohen's rules of thumb for each of his different metrics for effect size are in wide use, and his metrics for Cohen's d, his standards for Cohen's d was that if we have a small, a medium, and a large effect size for Cohen's d, we would expect to see a 0.2, 0.5, or a 0.8 effect size. So this effect size, what this shows is two samples, shows the frequency on the y-axis here, and the means are shown by these lines here. It's mean 1 and mean 2, and the variance around those means and the overlap shown by them is illustrated by the Gaussian curve. What this shows is a difference between these two samples quantified by Cohen's d of 0.9. So that's a little bit bigger than the standard rule of thumb for a large difference. Now, a totally different one, we haven't talked about all of them. There are many of them, and kind of confusingly for when you're first learning this stuff, each one of them can be calculated in multiple ways, but I just want to show you another common effect size. So another common effect size is the correlation coefficient. It's R, or sometimes I like to call it little r, so there's no confusing it with big R squared. You can see for a correlation, the effect size is the correlation coefficient. And for relatively high correlation of 0.7, you can see what that means. This is a positive 0.7 correlation. And if we reduce the effect size to 0.3, you can see there's a much bigger spread. And if we reduce it completely to 0, it's just a shotgun blast on the graph, and then negative ones down here and so forth. So for a simple correlation, it's simply the correlation coefficient. Now, these are two that are often cited, the Cohen's d and the correlation coefficient. But for most of you guys will be doing experiments that are more complicated than the very basics of one-way ANOVA, t-test, and correlation coefficient, and you can't use those. Yet we have to talk about them when we start there, and there are rules of thumb that exploit them for more complicated designs. But this paper is my very favorite paper that I do believe every PhD student should read here at Harper and everywhere else, because it's very practical. It accounts for every kind of linear model that you will ever design an experiment to be, and it uses Cohen's F squared as a effect size measure. Cohen's F squared is not easy to calculate, and there are many ways to calculate it. And yet, this paper explains it in a very simple way and gives you one or two methods that are foolproof. The only thing you need is the pilot data or the bravery to estimate the numbers that you need to go into the F squared. And just to give you an example of how easy it can be, is if you have a linear model, it could be a mixed effects model, it could be three-way ANOVA, it doesn't matter. If you can estimate how much variation, how much variance your total model will explain, even if you can guess, you can calculate, you can estimate the F squared. The way that I like to calculate the F squared is to come up with your estimate of your R squared, and it's the R squared divided by 1 minus your R squared. So if you think you're explaining half the variance or 60% of the variance, you can calculate the estimate of your F squared. And from that, it's quite easy to calculate the power and the sample size you need for a given power. So I would recommend this paper. We're not going to look at it today. How do you calculate this stuff is another thing that I mentioned. I've gotten a swath of requests lately. So some of, I have a small role here. I think if Martin is still in the chat today, I'll say this for your benefit, is I have a very small sliver of my time that's devoted to doing power analysis with research students. I see your hand, thank you. I've calculated that the amount of time that I'm meant to spend doing this with research students is about 3% of my time, but I have also calculated how much time I actually spend doing it with colleagues and research students, and it's about 15% of my time, so quite a huge amount of my time. And at some parts of the year, it's busier than others. So one of the things I talk about with these guys is how to calculate power, so you could do it yourself the next time, or come to me to make the process faster the next time. And well, this is a very short blast, and I will give a demonstration of one of these today. One way you can do it is in R. All the simple effect sizes is just to use R. It's very simple. I've demonstrated it many times in here when people have come to visit in the Herod groups. And I use the PWR package. It's a direct derivation of Jacob Cohen's simple rules. One that I sometimes use for slightly more complicated questions is trial size. It is very easy to use, and one that has agriculture designs in it is Agricole. This one is a big rambling package that has just a lot of gold in it and a big sample of ore. You have to dig for the gold sometimes in it, but I love the package. It's really, really crazy good. The one I'm going to demonstrate today, though, is my favorite high-powered effect size calculator called G-Power. This is a power calculator for connoisseurs of experimental design. It's a standalone Windows app. It's free, but it is kind of hard to use correctly for non-statisticians. I generally mention it, but don't recommend it for other people. Another one I have considered asking Martin or other generous people to buy for me here, since I do so much of this kind of work, is Pass. I have done some time with the Pass software in the past. It's a Windows app. It's quite expensive, and I can do these calculations by hand and with R and G power. So it's not a huge motivation, but I sometimes have begun to think that it could be faster for me to work. It's expensive, but it's much easier to do than G power, especially if I think they brag that they used to brag that they could solve power for 1,000 different experimental designs. So maybe it's up to 1,200 now since I've used it last. But I see people using in earnest are rules of thumb, and there used to be a literature. I'd say that I became aware of this literature as a student in lectures myself as a statistics student. And this literature came from the applied sciences, and it was quite besmirched by academic statisticians. So what I was taught as a student was that these rules of thumb, we can't promote this stuff. It's easy to misuse. It's treated like a magic bullet, and if you already can't do it the right way and can't consult with a real statistician, there's no helping you. That's kind of the message my statistics lecturers gave to me back then when I was a PhD student. I myself have come to that same opinion, and it's gotten, as I've seen the application of rules of thumb over the years, I think I can't recommend them. But there is a literature on it, and even some applied textbooks have rules of thumb, and indeed Jacob Cohen's rules of thumb. Key message that I want to leave you with: the effect size is tied to your statistical design. So you have to know your statistical design to get help on this. Key message 2, this is tied to your statistical question. So to calculate your effect size, you have to start with that question and be able to articulate it with some estimates of the starting values that we need, like the variation and the mean differences. And then last, rules of thumb don't work. Don't use them. Now I'm going to leave you on that slide and come back to you later and pass it over to Charlotte for a moment. I'm going to pop up your slides, and she's going to tell us about her experiment. I'm just going to share this and slide away. And I'm going to change the presenter, and those guys can see. And I'm just going to move away and invite Charlotte in.
Hello. So as Ed said, I have got a dairy cow study coming up. It's looking at methane emissions in dairy cows and using essential oils to see if we can reduce the amount of methane produced. So the title of my study is The Effect of Essential Oils When Supplied in a Slow-Release Rumen Bolus on Methane Production in High-Yielding Dairy Cows. So I'm just going to talk a bit about the study design and what we came to Ed to find out. Do I?
If you just, sorry.
It's okay. Just click it. Oh. So the main objective of the study is to determine whether the essential oils supplied either in the feed or in a rumen bolus and the effect on methane production and also the performance of high-yielding dairy cows. There's quite a few aspects to this study in terms of performance, but the main sort of objective is to look at the methane production. So just a quick overall view on the study design. We are planning to have 45 cows in total, and they will be split into 3 treatment groups, so 15 cows per group. We'll have a control group that will just be fed the basal mixed ration farm. we'll have a group that will be fed the essential oils in the feed, and we'll have a third group which will have the essential oils in the bolus. Before the study commences, we are planning to have a 2-week covariate period where we will measure the milk yield, weigh the cows, body condition score them, and we will also begin to take methane emission measurements. And then the idea is that data from that 2-week period will allow us to allocate the cows to the treatments based on that data. So then we can kind of get an even spread, and we're not accidentally putting all the cows with high milk yields on one and all the ones with a low yield on the other. So just a bit more on the design. Once the 2-week covariate period is finished, the cows will start on the study, and that's when the treatments will be put into place, and they'll remain on that study for 10 weeks. All of the 45 cows will be milk sampled weekly and the milk analysis composition analysed. 10 cows per treatment will be blood sampled fortnightly. Live weights, body condition scores will be collected from all the cows fortnightly, and we'll also be collecting fecal samples from 10 cows per treatment in week 8. Now coming on to the methane measurement side of things, the methane samples will be collected via a system called the green feed systems, which is something we've had recently fitted. And this diagram there is just a bit, shows you how they work really. There's been quite a lot of work done on them, using them, but it's the first time we've had them at Harper, so it's a very new area that we're looking at in terms of how to measure the methane. Looking at the literature, we're expecting the methane measurements to be about 450 grams per day. They do vary, but that appears to be the average for sort of a dairy cow in the UK. We're expecting a difference in methane results between the treatments of up to 15%, say around between 10 and 15, but 15 is sort of the highest difference we're expecting. And having looked at similar studies also investigating methane emissions using the green feed systems with dairy cows, they usually find an SEM of around 12. And this is the information that we came to Ed with, to sort of try and work out.
I didn't even have to ask for it. Amazing that you brought it.
To work out how many cows we would statistically need to get the methane samples from for it to be statistically valid. And I think that's my last slide.
Okay.
So hopefully that just gives you a bit of an idea of what the study will be. And
yes.
Okay then.
Yeah, we're changing back. All right, so let me just check our time here. Amazing. We still have 20 minutes to talk about this calculation. It's actually quite simple. I'm not going to show a lot of R code today. In fact, I'm not going to show any R code today. I'm just going to talk you through what I did. I'm going to reshare my slides. Now, if anybody who is out there, and I know there are a lot of you who have come to visit me, you may recognize this image. Not the exact image, but you may know what it is an image of, because you know that I obsessively use that whiteboard for all sorts of things. And when you come with an experimental design question, I will draw your experimental design, make mistakes, probe you, and get the essentials of it out. I wanted to show that process here, because almost the first thing that I ask people when they come to see me is, can you draw a picture of what you expect your experiment to go? This is kind of a way of thinking about it, and it's a way of setting yourself up for an effect size. Let me just turn on my pen again, and I'll make a few annotations on this before I go on. There we go. So what I've drawn here is what Charlotte said verbally. It's got all of the essential details that she said. Now, one is that I've drawn a picture down here of a graph that would represent the results of this experiment. We're imagining the results at this point, but this is some measurement of, I think I recall that there were several measurements of that were dependent variables, but one was the methane out. And we know the scale of the methane, that the control variable here, T1, is the control. And then these are the two treatments for organic oils. Maybe we call them, organic 1, organic 2 kind of thing. We know that that on the y-axis, this value is approximately 450. And we know that there's some kind of difference here. I noticed on your slide that you put 15% difference. Up to 15%.
Sort of the highest it could be, but 10 to 15 is the is what we expect.
That's what we expect.
Yes.
So that's what you clearly said that day, and that was quite good. And furthermore, you had an estimate of the standard error of the mean, which is kind of like the standard deviation divided by the sample size. We got this, there's some conventions here. If you do sample size determination through power analysis that are, I want to point out, before I do that, I want to say one other thing that you did also say in your slides here, that that you already have an idea of how many subjects you're going to have. And so really my role in this, one way, a cynical way to view this is that I don't really have a role because you have already decided your sample size. But actually there is a specific role for the power size justification here. We still would like to know whether your planned sample size is big enough.
Yeah, because you could always change it if you came back and said it's completely,
That's right. That's right. And another thing that we must know is that for we have an animal science. Some of you guys will know this because you work on animals already, and some of you guys may not know this, but there is an animal ethics committee that's a legal entity with named roles here at the university. Here, I can never remember what the acronym stands for, but it's the AWERB committee. Kind of looks like this. AWERB. This is a regulated body, a panel of experts here at the university. The panel is comprised of people who hold animal licenses, and they represent people like Charlotte doing experiments with animals. It is people like, there's a named vet on the board, named members of the public, named animal experts, and there's a named biostatistician. I'm the named biostatistician here. So the other reason to do this one is to make sure that the sample size doesn't exceed the minimum number that is needed to do it. We have to justify all of the animals we do to minimize the ethical impact on the animals. Okay, so we have all the information that we need for a power analysis here, including the variation and the difference in means and the magnitude of the means. Now there is one little bit that we don't have information on that's on this slide, but I knew when we had the consultation that there was a reference literature that I could look at for similar experiments in Charlotte's lab that I was aware of, and so I did volunteer myself to look in there, and that's because this is a mixed effects design where each individual cow will be measured multiple times. And so the sample size has to be accounted for that. And the thing that I need for the sample size calculation from the mixed effects design is I need to have some idea of the correlation between measures for individual cows. And so I was able to estimate that from looking at the previous studies. I'll show you about that in just a moment. Here are just my thoughts. These are just brief notes. I usually would put notes like this into an R script, but I chose to do, as I'll show you in a second, a different method of calculation today, and I will write this up in just a half pager as part of my role on AWERP to feed back to these guys for their proposal. So the control group is about 450 units for methane. And you expect the treatment groups to have about 10 to 15% lower. Now, I estimated the range of the treatments based on that 10 to 15%. But what I don't say on here is that I decided to go ahead and do the power analysis for 12.5%. So just the average of your expected. And sometimes you could do the range of expected values is a bit overkill for this one for reasons I'll explain in a second. Now the standard error of the mean is 12. This is another one of these kind of experiential places where I have to use my experience and expertise to make a judgment call here. We don't actually know the sample size. The number that we talked about verbally was 12. I could go back to the literature and try to derive this 12 myself, but then that's a lot of time and extra work to do that. Or I could estimate that remember the standard error of the mean is weighted by the size of the sample size used. So here, I know our target sample size is about 15 animals per group. And I just in my mind could do the calculation that if it's about 15, the square root of that is around 4, and 4 times the standard error of the mean is a pretty good approximation of what then we would expect the sample variance to be, the standard deviation that is for this experiment. So I could use 48, but there's actually a convention to use the standard error of the mean as a conservative value. So that's what I did in this one anyway. But again, I could make more realistic calculations. Now the statistic that I chose for this one is Cohen's F. I'm not going to give a whole lecture on Cohen's F because I want to show the G Power app, but Cohen's F can be derived just like, in fact, it can be derived from Cohen's D. And Cohen's D, if we just go back up for this experiment, would be conveniently, I find my pen again, there it is. We know that we can derive it from this variance and this difference, both of which we have. So it doesn't make sense for me to spend a lot of time pointing out how I got it, but I calculated Cohen's F. Now, the last thing I want to show here is just a screen, and I want to show it this way on this slide and make some annotations before we go to the actual app and have a play with some of the numbers ourselves. But for Cohen's F, the rules of thumb for Cohen's F are for small, medium, and large. They're approximately 0.15, 0.25, and 0.4. And you can see in this screen, I've put in 0.4, so large. Now, when I actually calculated Cohen's F for this, Cohen's little f for this, it was much larger than 0.4 given the numbers, but I've had to make some estimations here. So I've put in the critical amount of information that I put in. Let's come back to Cohen's F in just a moment. I've put in the alpha value as 0.05. And I guess I should say first, I'll demonstrate this just in a second, that I've chosen the statistical test. I called it a mixed effects model, but in the language of G Power, that's equivalent to an ANOVA, with repeated measures for between factor tests. Okay, so it's just a bit of jargon. Furthermore, I've chosen the family of tests of the F-test, which is for which Cohen's little f, not f squared, but Cohen's little f is appropriate. So those are the choices that I made prior to this screen. And the type of power analysis that we do, if you know the effect size, the sample size, and the power, if you know any two of those, you can calculate the third. And sometimes it's interesting, and there's a reason to explore all three of them. Not in this case, but sometimes. So that brings us down here. That gives you the options that are required for the calculation. The alpha value is always the default of 0.05 unless there's a good reason not to have it that way. The power we're shooting for this kind of experiment, we want to shoot for at least the minimum power, 0.8, and we did discuss it on the day, and that was the power that we wanted to shoot for. The number of groups are just the number of treatment variables, and that in this case is 3. The number of measurements, now this one we did talk about it, and I've left 5 in here, but it's up to 8, I believe, or even more than that. There was some number of weeks that you'll be measuring it. It doesn't have a big effect on the power, so it's one of the things we can play with in a moment. And the thing that we didn't really talk about, and I had to go to the literature for, was the expected correlation amongst measures. And what I estimate the correlation between the repeated measures. So this is the degree to which different cows emit different level. There might be some high burping cows, some medium burping cows, and some low burping cows. And it's a quantification of the correlation over time of an individual cow. So in a mixed effects model, if some of you have been in some of the talks we've done on this, in a mixed effects model, this correlation is the repeatability within individuals for whatever the random effect is. And it's pretty high as reported in the literature, and 0.5 is my best guess as to what it would be, but it could range from 0.2 or 0.3 up maybe to 0.6 or something. So I've estimated it here at 0.5, but that's something else that we could do. Now with this calculation, I just want to get rid of some of this confusing stuff. Once I have hit calculate, which I already have for this one, we get an estimate of what our ANOVA big F would be. And remember, this is a quantification of the within versus between variance for ANOVA kind of linear models. So the bigger this is than 1, the more likely it is to be a significant difference. It's calculated our degrees of freedom for us. That looks just fine. But critically, it's rounded the total sample size we need, rounded it up to achieve a minimum of 80% power. So the answer we want is really this 42. That's very satisfying because that's also the number from the meaning of life, if that means anything to any of you. And if we hit 42 total sample size, we get 82.9% power. Making these assumptions, let's just look at the G-Power program. Now the G-Power program is awfully small looking on my screen. So what I'm going to do is I'm going to unshare and just share that screen. I'm going to share a window and I'm going to share G-Power. I think that will look better for everybody. Can you guys see that?
Yeah, that's better.
Good. So what I would typically do is I would report this back as briefly as possible. I like to aim for a pager, 1A4 pager, where I will state the purpose in statistical terms of this experiment. I will state clearly the assumptions that I have made and the source of those assumptions. It's right and true that almost all of the assumptions come directly from the researcher themselves. One of the things that impedes this progress is it's often the case, and I'm not criticizing the situation, because it is the situation is that many researchers are not aware that that this world exists, and so really the first part of the conversation is education. But when I have done this, I would report back the assumptions in my words that come straight from the researcher. And the last thing, I guess, is that I do have a source for the correlation assumption amongst them. Now, it's typical, if we were to alter this, the effect size I actually calculated was quite a bit bigger than 0.4. So what I might do is I might say, well, what if I calculated the effect size for 0.5? I was a little now 0.5 is a lot bigger than 0.4. It's 25% bigger. If I calculate that, the required sample size is only 27. But if I'm wrong on some of my assumptions, just a little bit, maybe it's down to 0.38, and I calculate that leaves the sample size at 45. Or if I'm down to 35, calculate total sample size of 51. So we can explore how variation in the assumptions impacts the required sample size, which is a typical thing to do with power analysis, and is what I will do on the one pager. The other one that I want to explore, if I just change this back to 0.40, which is the reason I chose 0.40 again, even though the calculated effect size was much bigger, is that this is one of the methods that statisticians use, that it's usually imprudent to assume that your effect size is much larger than one of the so-called rules of thumb, large category effect size. The reason for that is that it would not be typical to design a lot of experiments where that's the case, because if the effect size is so large that you barely need any sample size, it's almost an experiment that's not worth doing. So it is a rule of thumb that we go by, that we usually default as a conservative maximum, the rule of thumb, large effect size, like here. So the other assumption I've made is the correlation. I mentioned that it could range from 0.3. So let's see what a correlation of 0.3 does to the sample size. So if there's low correlation for the sample size, it reduces it to 30. And if there's a high correlation, let's go up to 0.8. Well, I think 0.6 is the maximum that I would expect. It goes up just a little bit to 0.45. So I might explore that from 0.4, 0.5, and 0.6 to look at that range. So what I'm looking for, I'm just going to unshare my screen one more time, reshare it again, back to the slide. What I want to do is I'll just remove that and make sure I have my pin, and I do. There it is. So what we're looking at here is if we want to explore our our power as an effect of our sample size. And maybe this is the line where power is equal to 80%. And let's say that this power is for this one with effect size of 40. So what we might have here is our sample size. Let's put 42 there. And we have a dot there. And what I can do is I can begin to build, if I change the correlation amongst the reps, I just bring back G power. If I change the correlation amongst reps here to exactly 0.5, it brings us up to 42 where we are. And if I make it 0.6 and I calculate, brings us to 45, and that's at 80% power. 45, and so forth. And we could have a couple of lines on this graph to allow the researchers to choose the line that they want to the most. I think we're out of time. Looking at the old thing, I see a question from George. You want to share the source for the 0.5? Yeah, I can share that. That's one of Liam Sinclair's papers. Yes, I can share that. I haven't uploaded today's stuff, but I'll upload my slides, your slides, the F2 paper that I think all PhD students should read, and I'll also upload Liam's paper where that assumption came from. It's not going to, if you open up and read Liam's physiology paper, it's not going to say in the abstract, oh, and the intra-class correlation is 0.5. What it's going to say is it's going to have some ANOVA tables with degrees of freedom and the amount of variance explained. And then there's going to be some variance in the graphs. And I made an inference by doing some calculations to come up with that 0.5. So, but yes, you can have a look at it. Any comments or questions? Thanks. I'm glad you enjoyed it, George. Any comments?
I think, sorry, so what you just said then about being able to infer that intraclass correlation to get 0.5 from that data, I think it would be really interesting for me especially to see how you kind of did that from taking that information from the paper, just because I've always had a vague understanding of effect size and power, but it, like, one thing that's made it really clear that you've mentioned is it is, if you've got pilot data and it is actually looking at or knowledge that's already out there. And I think because no one's really ever stated that before, it's always been like a grey area, and it's like, but you know, you have to take responsibility for it and, you know, read the literature and stuff. So yeah, thank you.
Yeah, where it comes, where I would prefer it to come from is for a mixed effects study. And that's where you need this correlation for the repeated measures. Where I would prefer it to come from is pilot data. And in pilot data, I mean, I do actually have some pilot data that I didn't resort to from a previous work I did with Liam a couple of times. But if you have a mixed effects model and you have a random effect, in this case represented by the individual cow, which is the repeated unit of repeated measures, what the way you would derive a direct estimate of it is you would run the model and look at the residual variance due to that individual cow for the random effect and divide it by the total residual variance for the whole model. And that literally is a proportion of variance due to the individual repeated measures, which is a surrogate for this correlation for an ANOVA model. But that's the way I would prefer to do it, to have pilot data, or to have the researcher turned on enough to say, yeah, I know you need the correlation and it's 0.41. But it almost never happens. So we have to derive it or estimate it, which is what I did here. I don't have the data that I have. The previous data that I have is not on methane emissions. It was on other metabolic function, and actually, come to think of it, it's also not about organic oils. So it is quite a different study. It just represents how similar cows are one another in feed experiments. So I have only crudely estimated this, and that begs the question of how much we should model around the assumption, which is really a question. It's a problem for the researcher. The researcher has to evaluate that for themselves. I can't do that because I'm not an expert in methane emissions in cows. So there are a lot of subtleties to it, and experience is a part of it. Any other comments or questions? I'm just going to stop the recording now.